Dear students, in the last video we have studied about the IR spectroscopy, rotational spectra and vibrational spectra. When in the rotational spectra and vibrational spectra, when the molecule is irradiated with infrared radiation, there is excitation in the rotational level as well as in the vibrational level. So this is vibrational level, this is rotational level. So rotational spectra and vibrational spectra are produced because of irradiation of infrared radiation on the molecules. At the same time, it has been observed by Sir C.V. Raman that when the molecules are irradiated with infrared spectra, apart from the transmittance of light without any change in the rotation, apart from absorption and emission of light by the molecule, it has been observed that some amount of the radiation is scattered. Some amount of the radiation is scattered at 90 degree, at right angles to the incident radiation. If this is the incident radiation of frequency nu, when that frequency is incidented, a majority of the rays are transmitted or absorbed and emitted by the molecule, but some amount of radiation is scattered at right angles to the direction of the incident radiation, and it has been observed that this scattered radiation has different frequency or different wavelength than this incident radiation. So this effect, the change in the frequency of the scattered radiation, is called Raman effect. So Raman effect is the change in the frequency of the incident radiation. When the molecule is irradiated, when the radiation is irradiated on the molecule, the wavelength or the frequency of the radiation which is incident changes its frequency, either increased or decreased. That is called Raman effect. So Raman effect is resulted in the decrease in the energy or increase in the energy of the radiation. Now, when it is observed, these radiations, scattered radiation, it has been observed that there are three types of scattered radiation. One group of radiations, they have less energy than the incident radiation. So incident radiation, suppose if nu I is the incident radiation, it is equal to nu scattered radiation minus energy. So energy is decreased in the scattered radiation, energy is reduced in the scattered radiation. So therefore, this produces a group of lines, a band of lines, a group of lines in the spectra. That group of lines is called Stokes lines, where majority, more number of radiations, they are diffracted. Those diffracted radiation, they have got less energy, less frequency than the incident radiation. Those are called Stokes lines. And some of the radiations which are scattered here, the scattered radiation has got the same frequency as the incident radiation without any change in the incident radiation. A group of lines, a band of lines are obtained, that is called Rayleigh scattering. And another small amount of radiation, majority of the radiations, they come out having less energy, whereas a small portion of the incident radiation or incident radiation come out with higher energy than the incident radiation. So therefore, in this case, this is called anti-Stokes lines, where there is high energy and frequency is increased. So that can be represented by Ri is equal to frequency of the scattered radiation plus energy. So these have got high energy, higher frequency or higher energy than the incident radiation. Therefore, three groups of lines are observed in the spectra. This is called Raman spectra. Raman spectra. So Raman spectra is a band spectra. It consists of three major bands. One band without any change in the frequency, that is called Rayleigh scattering band, and another one is another group of lines which have got less energy than the incident radiation, they are called Stokes lines, and a small amount of the radiation which is scattered, they have got more energy than the incident line. They are called anti-Stokes lines. So these three groups of lines are the characteristic of Raman spectra. So there is a change in the frequency towards left or towards right. This change in the frequency is called Raman effect. So therefore, this Raman spectra is very helpful in determining the structure of the molecule, and this Raman spectra is obtained not only in the infrared region, it is possible in the visible region. So apart from IR region, we can use visible radiation to find out the Raman spectra, and in some cases, in some molecules, it is also possible to get Raman spectra in the ultraviolet region. A large range of radiation is possible. It is possible to get Raman spectra in the long range of electromagnetic radiations, that is IR, visible and UV radiation. Now, to explain this Raman effect, change in the frequency of the incident radiation, Raman effect. To explain this Raman effect, two theories have been proposed. One theory, first theory is called quantum theory. Quantum theory. According to this quantum theory, electromagnetic radiation consists of quantas having energy E is equal to h nu. When radiation is irradiated on the molecule, these quantas are also called photons. These photons will collide with the molecule. When collision takes place between the molecules and the photons, these molecules, they undergo excitation. These photons which interacts with the molecules, there are two possibilities for these photons. These photons can lose energy, and thus energy is acquired by the molecule. Therefore, these photons which comes out after irradiation, the frequency of the photons which are scattered, they have less energy. Because the molecule absorb energy from the photons, and the photons lose energy and come out with lesser energy, and those photons which come out of the molecule is responsible for these Stokes lines. Stokes lines, they are due to the absorption of energy by the molecule. Therefore, Stokes lines are observed. In some cases, the molecules collide with the photons. There is a collision takes place between the photons and the molecules. Those collisions, they do not gain or lose energy. They are called elastic collisions. So in this elastic collision, perfectly elastic. There is no gain or loss of energy to the photon. When the photons collide on the molecule, collision takes place and it will be re-emitted. When they re-emit, because the collision is perfectly elastic, there is no loss or gain of energy. Therefore, those elastic collisions, they give out the photons which are irradiated on them, and those lines, emission of radiation, emission of energy by the elastic collisions are responsible for Rayleigh scattering. Whereas in case of anti-Stokes lines, when the photons collide on the molecule, those molecules, they are already in the excited state. Some molecules, they are in the excited state. They are energetic in their molecular state. When these molecules are irradiated with the infrared radiation, these molecules which are already excited, they have got higher energy, they give some amount of energy to the radiation. So therefore, in this case, frequency of the incident radiation is equal to frequency of the scattered radiation plus energy. Some amount of energy is acquired by the photons. Therefore, the frequency of the scattered light has got more energy. Therefore, we get radiation, we get a band of anti-Stokes lines, and these are due to non-elastic or inelastic collision. Inelastic collision. So, inelastic collisions are responsible for Stokes lines and anti-Stokes lines. So, inelastic collision are responsible for Stokes lines and anti-Stokes lines. In case of inelastic collision or non-elastic collision, energy is gained or lost. The photons, they lose energy or gain energy due to collisions. So, if they lose energy, energy will be less. So, energy will be less. The molecules absorb energy. Those are responsible for the Stokes lines. When the energy is gained by the photons, energy is absorbed from the molecule by the photons. So, those radiation which come out, they have got higher energy, higher frequency, and those are responsible for these anti-Stokes lines. So, that is the theory, quantum theory of Raman spectra. So, there is another theory to explain this Raman spectra. Why there are three types of bands in case of Raman spectra. There is another theory that is called classical theory of Raman spectra. In this classical theory of Raman spectra, it is assumed that the radiation, IR, visible or UV radiation, they are electromagnetic in nature. That means they have got electric field as well as magnetic field. So, this electric field is responsible for different types of lines in Raman spectroscopy. The electric field of the radiation will interact with the molecule, and the electric field interact with the molecule and makes this molecule a polar molecule. So, this molecule becomes polar. This is non-polar. Now, this becomes polar molecule. That is called polarizability. So, this electric field of the electromagnetic radiation, which irradiated on the molecule, it causes polarizability in the molecule. It makes the molecule polarized, polar molecule. So, this polar molecule takes place. Polar molecule has got dipole moment. Therefore, this has got dipole moment. Dipole moment has got direction. So, therefore, when the radiation is irradiated on this molecule, the electric field of electromagnetic radiation interact with the charged end of the molecule. Suppose if the electric field react with the negative pole of the molecule, repulsion takes place. Therefore, energy will be more. Suppose if it attacks the positive end of the polar molecule, attraction takes place, energy is reduced. Therefore, repulsion and attraction between the electromagnetic radiation and the polar molecule is responsible for these Raman spectra according to the classical theory. So, the classical theory tells you about the interaction between the electric field of the both molecules and electromagnetic radiation. So, polarizability created by the electromagnetic radiation is responsible for this Stokes lines, anti-Stokes and Rayleigh lines. Suppose if there is interaction between negative electric field and the negative pole, equal same charges, repulsion takes place, energy will be more. Therefore, emitted radiation has got more energy. If there is attraction, energy will be less. And if the molecule is not in its direction, either a negative direction or positive direction, if it is perpendicular to the direction of the radiation, then there is no absorption, there is no repulsion or attraction of the electric field. Those radiations will be emitted with the same amount of energy, and that is responsible for Rayleigh scattering. Repulsive force is responsible for anti-Stokes lines, and attractive force is responsible for Stokes lines. So this is the explanation by classical theory of Raman spectroscopy and quantum theory. There are two theories which explains the Raman spectroscopy. So, according to quantum theory, the radiation, when irradiated on a molecule, it absorbs, according to quantum theory, it absorbs quantas, because the radiations are made up of particles called quantas. Energy of a quanta is equal to h nu. Therefore, these energy packets, energy quantas, are absorbed by the molecule. So, according to the quantum theory, Stokes lines, Rayleigh lines, and anti-Stokes lines are due to the absorption of radiation of from the quanta, and emits radiation with lesser frequency. So therefore, some amount of the energy goes into the molecule. So this radiations, these Raman lines, in these Raman lines, majority of the Raman lines, they have got less energy than the irradiate radiation. So this is the frequency of the incident radiation. The frequency of the incident radiation, from this radiation, the molecules absorb a few quantas of energy. Therefore, the energy emitted, the energy of the this molecule, Raman lines, they have got less energy. Therefore, these Stokes lines are due to absorption of more energy and the emission of less energy. In case of Rayleigh band, there is no absorption, there is no change in the absorption or emission of energy, and this is elastic collision. So elastic collisions are responsible for Rayleigh scattering. So diagrammatically it can be shown like this. It absorbs the energy here, and the absorption energy, absorption radiation, now the number of quantas absorbed is re-emitted back. Therefore, there is no change in the energy or frequency of the incident radiation and the emitted radiation. Though the scattered frequency of the scattered lines, and frequency of the incident radiation are one and the same, and that is responsible for Rayleigh lines. So diagrammatically it can be shown like this. So this is Rayleigh lines. In case of anti-Stokes lines, the frequency of the incident radiation and frequency of the emitted radiation are different. The frequency of the emitted radiation is more than the incident radiation, because some amount of the energy is absorbed from the molecule by the quanta itself. Quanta absorbs little energy from the molecule, because the molecules are already excited. Therefore, some amount of energy is absorbed by the radiation, and the frequency of the radiation is more when compared to the incident radiation. So this is the frequency of the incident radiation, this is the frequency of the emitted radiation. Therefore, these anti-Stokes lines and the Stokes lines are due to inelastic collision, as we have discussed. So according to classical theory, this is quantum theory. According to classical theory, what happens? According to classical theory, as we have discussed, these electromagnetic radiations, they create polarizability in the molecule, and that polarizability is due to the dipole moment caused by the interaction of electric field of the electromagnetic radiation with the molecule. Molecule becomes polarizable. So polarization takes place, delta minus delta plus, polarization takes place. That polarizability, so therefore dipole moment mu is proportional to the energy of the electric field, electrical energy of the radiation, and mu is proportional to E, where alpha is the polarizability. Alpha is the polarizability, and that can be calculated using this equation, E is equal to E naught sin 2 pi nu t, and you can substitute E here. Therefore, this dipole moment can be calculated, and polarizability caused by the irradiation of electromagnetic radiation can be calculated. So in this case, if you see the Stokes lines and anti-Stokes lines, so this is the ground state. In the ground state, when the excitation takes place from Stokes lines to anti-Stokes lines, one this side and one that side, there are two shifts here, two shifts. Therefore, the frequency delta J is equal to plus or minus 2, whereas in case of rotational spectra, delta J is equal to plus or minus 1, there is only one stage of excitation. There is only excitation from one level to next level. Here two shifts, two level excitation takes place. Therefore, the selection rule for Raman spectra, delta J is equal to plus or minus 2, whereas for IR spectra, delta J is equal to plus or minus 1. That is the difference between the selection rule of Raman spectra, Raman lines, and infrared radiations. That is there. Now, let us see the applications of Raman spectroscopy. So, this Raman spectra can be studied both in gaseous state and liquid state, and also in the solid state. Whereas IR spectra only, it can be studied only in case of gaseous molecules. That too, the molecules should be polar in nature. Only polar molecules can be studied. Polar and gaseous molecules can be studied. For example, in the study of HCl, that can the HCl or any polar molecule having dipole moment can be studied by IR spectra. Whereas in Raman spectroscopy, it creates polarizability. It creates dipole moment. Therefore, homonuclear molecules like nitrogen, oxygen, etc. can be studied, and the structure can be can be found by this Raman spectra, and also the Raman that is in Raman spectroscopy, polarizability is created. Therefore, homonuclear molecules can be studied, whereas in IR it is not possible to study the IR spectra of homonuclear molecules. It is not possible. That is the application advantage of this Raman spectroscopy. Another important application of this Raman spectroscopy is double transition takes place. Therefore, you will get a clear line in the Raman spectroscopy, whereas here in case of IR spectroscopy, there is a bands of lines there. So here this selection rule is delta J is equal to plus or minus 2. So double transition takes place. Therefore, the lines are very clearly we can study that Raman spectra. And another important thing is, in the study of IR spectroscopy, we use microwave region and far infrared region only. So rotational spectra takes place in the microwave region, whereas vibrational spectra, it takes place usually in the far infrared region. Therefore, it is difficult to analyze those radiations in the microwave region and the far infrared radiation. Whereas in case of Raman spectra, we can use near infrared region and also visible radiation. Because we can use visible radiation, the study of the spectra is very easy for us. Therefore, this Raman spectroscopy can be studied comfortably by using visible radiation. That is another important advantage. In microwave only, you have far infrared and micro region in case of IR. So Raman spectroscopy is very convenient. And even as I told you earlier, the solids and aqueous solutions can be studied by Raman spectroscopy. Solids and homonuclear gaseous molecules, aqueous solutions can be studied. Whereas this infrared spectra is opaque to water. Therefore, aqueous solutions of the molecules, aqueous solution of the substances cannot be studied by this Raman, IR spectra. In Raman spectra, we can study aqueous solutions, solids, homonuclear, gaseous molecule, all of them can be studied here. These are some of the advantages of this Raman spectroscopy. Now, let us see how this is helpful in solving the problems. So, let us solve a problem. This problem is, if HCl35 isotopic is 35 normal, HCl is irradiated with radiation of wavelength, is given wavelength 4.368 10 to the power of minus 7 meters. So, in wavelength it is given, but they asked to calculate the Raman line if the vibrational frequency, so they have given frequency. So irradiated electromagnetic radiation is given in wavelength values, and the spectral line, it is given in the frequency. Therefore, let us convert this wavelength into frequency. So, given wavelength is equal to 4.368 10 to the power of minus 7 meter. Now, you convert that into frequency. We know that C is equal to nu lambda. Therefore, if we know lambda, we can find out a frequency. Frequency is equal to C by lambda, 3 into 10 to the power of 8 meter per second divided by lambda is given. This is the velocity of light. C is the velocity of light, 3 into 10 to the power of 8 meter per second. And this wavelength is given here. You see, if you substitute there, you can find out the frequency of the incident radiation to produce Raman line. Incident radiation frequency. So here we have converted wavelength into frequency, that is 6.86 10 to the power of 14 per second. And we know that for Stokes lines, Raman to get Raman lines, the frequency of the Raman line, if it is less than the frequency of the incident radiation, it is called Stokes lines. Now, incident radiation is given, frequency of the incident rays are given, and also frequency of the spectral line, Raman spectra, is given. Now, let us take the difference between the frequency of the incident line minus frequency of the scattered line. Frequency of the scattered line. Now, that difference gives you delta nu. That can be calculated by deducting delta S minus delta minus. So, therefore, the Stokes lines, they are observed at frequency 60 into 60.028 into 10 to the power of 13. So, Stokes lines, it is given in frequency. Frequency of the Stokes line is given. We can convert this frequency into wavelength, because they have asked here calculate the Raman line in meter also we can calculate. So this is the Stokes lines in the Raman spectra. Now let us convert this into wavelength. Stokes lines is given in frequency. We know that C is equal to nu lambda. We know frequency. So velocity of light is 3 into 10 to the power of 8 meter, and frequency of the Raman line is given here. So if you divide one by the other, you will get the wavelength of the Stokes lines. So wavelength of the Stokes lines is this, and this is the frequency of the Stokes lines. Therefore, we can calculate the Stokes lines, and from these values, we can find out the structures of the molecule in this infrared Raman spectroscopy.